Hi everyone, my name is Sylvain Lézé from the Department of Aeronautics at Imperial College London in the UK, and this is the new episode of the podcast Turbulence at the Exascale. So if you're not familiar with the podcast, we are trying to gather the view of the scientific community regarding the challenges and opportunities that will come with exascale computing, with a particular focus on turbulent flow. So this podcast is organized by the UK Turbulence Consortium and is also part of the UK initiative called ExCALIBUR, which is a 5-year project aimed to redesign software production codes in the UK for the transition to exascale computing. So today our guest is Tobias Grosser, who is a reader in compilers and runtime systems in the School of Informatics at the University of Edinburgh. So good afternoon, Tobias.
Yeah, good afternoon. Thank you for the invitation to this podcast.
Thank you very much for joining us today. So I didn't say, but Tobias has interest in compilation programming, languages design, and effective performance programming on high-performance computers. And this is the reason why we have him as a guest today. So Tobias, can you tell us a little bit more about yourself, where you are from, what you have studied, and how did you end up in Edinburgh?
Yeah, so I'm born in Munich from Bavaria, Germany, and I studied at least my bachelor's in Germany, in Passau, a very small city close to the Austrian border, beautifully located right next to a river. And so kind of this actually inspired a lot of my later career. So I happened to have another degree on intercultural studies, which really inspired me to move around the world. And so I moved to Argentina, stayed for several internships in the US, Austin, Columbus, the Bay Area, and then eventually also Cambridge, UK. And basically then this, like for my PhD, this kind of put the vision into my head that I want to use my PhD to get to know another culture. So China was one very interesting option, and France was the other. And because I was just getting to know LVM, and at that point this was the new exciting thing for me, I was looking for a PhD opportunity in that space, and in China that was not yet so well known. And so I got a really nice offer from Albert Cohen, who just said, I met him in an open source meeting, and he just said, why don't you just, like, if you want to do a PhD, just come and do whatever you want. And I thought that was a good offer. And
that's a good offer indeed.
Exactly. Yeah.
Excellent. And may I ask you, how did you become interested in, so I mean, you mentioned your different research interests, but how did you become interested in high performance computing, programming language design, and software development?
Yeah, I think it started really in the second week of my bachelor studies. So it's very interesting. Like one of the professors asked if I want to do like a small student project, and I thought it's a good idea. So I walked to his office, and so this professor was called Martin Griebel, and he had this list of open student projects, like 10 projects. And at the very end, there was his kind of project titled Dream, bring polyhedral constraint-based loop transformations into open source compilers, such as GCC. And I think he wasn't really believing that any student wants to pick that up, but I found that quite intriguing. And so I decided that's a good first project to start off with. And he introduced me to the open source community, and I spent, I think, 5 to 10 years on trying to implement that project. And I'm still, like, part of my research is still in that space. So that got me hooked. And what kept me on the kind of like doing this kind of research was really this kind of open source environment. So I find it an incredible tool to kind of transfer and evolve knowledge. And yeah, this community in general, and then like the community interactions that you have day to day, I think that's what really keeps me going.
Great, thank you. And so you said you have been traveling a lot all over the world, and well, now you're in Edinburgh. So my next question is, what do you really like about your current position and about working at the University of Edinburgh?
Yeah, so in general, I mean, what the one thing I think most academics, or at least the thing I find personally most inspiring, really, is just to sit together with like students, postdocs, and other academics, and just have this joy of like having an idea, exploring a question, and working through these nitty-gritty details of like how can we make things work. And I think this is kind of like this seed of excitement, and then scaling that up to like collaborate with more people and actually like interacting with communities and really like starting to feel what we need or what different people need and try to come up with a solution that works for most people or kind of brings us forward. I think that this is kind of the challenge that I'm looking for. And I think Edinburgh is great because, I mean, there are a lot of interesting people, and particularly in the areas I'm really interested in. So we have a lot of compilers, hardware people. We have an amazing programming language group. We have HPC, we have design informatics. So a lot of the human compiler interaction or human computer interaction that I think will become more and more relevant is also here in terms of expertise. And kind of my small, tiny side joy in Edinburgh is that it also has a really interesting psychology department. So a lot of like, kind of like, if you think about like, how do we actually do science? There are a lot of like possibilities to learn about, but for example, like one part of this psychology department here is performance psychology, so sports psychology. How do people deliver excellent sport while kind of not being overstressed? And so that's really interesting to listen to and learn about.
Great, thank you very much. May I ask you if you can introduce your current projects you are working on, like just briefly to know roughly what you are working on at the moment? Yeah,
so I'm actually working currently almost across the entire technology stack from like compilers for hardware designs, so RTL designs, Verilog designs, over GPU optimization, up to domain-specific languages like mathematical expression languages for finite difference equations, for example, but also kind of as an orthogonal space and into interactive theory improvers, more formal languages, functional programming, and in some way that looks very unfocused. So the combining theme of all these things is really we've been working a lot on SSA-based static compilers and in particular domain-specific rewriting. And so the big picture, the big vision of what I'm working on is building these kind of like domain-specific rewriting systems across domains, but in a kind of compatible way, such that we kind of plug and play different rewrite systems from different domains and build tools that today I think are really hard to build, but in the future maybe it becomes a lot easier.
Great, thank you very much. Let's talk a little bit in more detail about your involvement with the ExCALIBUR project. So you recently got awarded what they have been calling a cross-cutting project around domain-specific languages. So can you tell us a little bit more about this project and what you are aiming to do within the time frame of the project?
Yeah, so this project is called XDSL for cross-domain specific languages. It's a compiler framework aimed at facilitating the design of domain-specific languages. And the key idea really is that we want to bring together the static compilation community that developed in this LLVM ecosystem over the last 10, 15 years. And in particular, a sub-project in that space, which is MLIR, it's a framework to instantiate static compilers, but bring it a lot closer to the Python ecosystem, which has been really impactful in being a foundation for many HPC domain-specific languages. And so we want to find ways to exploit synergies between these communities. So make it really easy for HPC or in general, any domain-specific language designer to take advantage of all the, especially target knowledge, GPU backends, maybe even more advanced AI backends that are available in the MLIR and LVM ecosystem and make these very easily accessible from the Python ecosystem. So we've been pairing up with various collaborators, so the DeVito team at Imperial with Jared Gorman and Paul Kelly, providing expertise from the computational science domain. And here in Edinburgh, I work with Michael Steuer, Nick Brown, and Emery Krause, also from EPCC. So we have a lot of HPC background as well as compiler knowledge. And yeah, I think we hope we can make some progress in this specific project. But I think the bigger picture really is, and then I think that what kind of makes ExCALIBUR special, is that this is not a kind of a standalone effort, right? In some way, we're going to be improving DeVito as a single DSL, but our bigger ambition really is not to create the next best DSL, but really almost like a non-ambition. In some way, it's a minor contribution, which we hope has a big impact. We want to factor out key building blocks that are useful across domains and make them available in this LVM ecosystem. And maybe these small building blocks, hopefully cleverly chosen and chosen with community input, make the design of DSLs easier and better for a lot more people in the ExCALIBUR system. So one specific work package, for example, we have is the work package to collaborate very closely with the Cyclone community, and to take the Cyclone Fortran-based software stack and bring some of the XDSL technology into this Cyclone code base, hopefully. Yeah, again, taking advantage of synergies that we can exploit.
Great. Well, thank you very much for the detail, and good luck with this very exciting project. Right, I've come across one of your recent paper called "Extracting Clean Performance Models from Tainted Programs," and I'm a little bit curious. Can you tell us a little bit more about that, and what you call tainted program and what you call clean performance model?
Yeah, it's actually it's an interesting paper, and so the objective for this paper was to take a large real world HPC software and derive a symbolic performance model. So concretely, you have an HPC program and a couple of input parameters that you define through some input file, and then you basically want to know what's the computational complexity of this complex program, right? So is it cubic, quadratic, or whatever the formula is, right? And so the formula is nice and clean, but if you look at real programs, they look, I mean, they have a lot of source code, but also from a compiler perspective, they are rather dirty in the sense that all these parameters get passed through data structure, through memory. It's really, really difficult to statically analyze these programs. And so the key idea of this paper really is that in computer security, you often need to understand what are the ways where certain security risks can enter a program or like a computer system. And so they developed this concept of a taint analysis, which allows you to accurately track the flow of a parameter throughout a program dynamically. And so we use this taint analysis concept to really track which parameter can impact which part of the program, and then use that to filter performance models and create cleaner performance models to give this really nice, pure performance prediction. Great,
thank you very much. Can you tell us a little bit about the Open Earth compiler, please?
Yeah, so this project is, I think, meanwhile, almost like, it's 1.5, almost 2 years old. And it's the very first project that I personally did on what's called the MLIR software stack. So was led by at this point, a PhD student and later postdoc who collaborated with me, Tobias Grosser. And the key idea is, Tobias Grosser had experience like 5 years ago to port the European Cosmo weather and climate model to GPUs for Meteor Swiss and CSCS. Mm-hmm. And we've been discussing basically since that day that we want to build an actual domain-specific compiler for that software stack. And when MLIR was released as a compiler stack, a static compiler stack for instantiated domain-specific compilers, we saw a big opportunity, not just for building yet another static compiler for Swift or whichever programming language, but really for this domain-specific compilation community. And so we paired up with different developers at Google and developed a stencil abstraction that captures the key insight of this like European climate model, but also various other abstractions. Among them is the GPU abstraction, for example, to abstract the code generation to GPUs. And I think this was really the key insight from that paper, that many people try to develop domain-specific compilers very successfully if there's sufficient funding and sufficient effort, but it's typically a huge amount of work. And so with this Open Earth compiler, we really demonstrated that developing a domain-specific compiler is still a lot of work, but 60 to 80% of that work is really in developing generic infrastructure, developing generic target backends, and there's only a rather small 20-30% fraction which is actually domain-specific. And so the outcome is it's actually like this compiler was faster than what Meteor Swiss and CSCS had at this point in running in production. But what I think is even more interesting, we contributed their GPU abstraction directly to the MLI ecosystem. This is now available in a production quality compiler stack. So any other domain-specific language that wants to do maybe climate, but maybe turbulent simulation or whatever other simulation really can take advantage of this GPU abstraction, which is maintained and evolved by the community. And it's basically, even if the Open Earth compiler may not be maintained further or going to be evolved in a different direction, the key shared abstractions are available and preserved for maybe not eternity, but for a longer period of time for other people to use.
Great. So it's still a project that is ongoing, and the compiler is maintained and improved, or this is.
So this is interesting because, and this really highlights the way how I do research. So the Open Earth compiler is a project repository. I don't think we really maintain that anymore. But in particular, what we did is we take the key ideas and really contribute them to living projects. So the GPU dialect is part of MLIR. A lot of the ideas of the stencil abstraction are now currently contributed by Tobias Grosser, who got hired by Google, into what's called the linear algebra dialect. It's kind of a generalization, a slightly different abstraction of these concepts, also available in MLIR. And many of the other concepts we basically live on in the XTSL project. And DeVito, for example, is one of these tools which can use very similar abstractions. So we're certainly going to be contributing some of these ideas also to DeVito.
Great, thank you very much. I've also seen that you have been working around neural network, and my next question is, you have been doing some work on neural network and computational memory accelerator. So can you tell us a little bit more about this?
Yeah, I mean, this was you're talking about a very specific paper, but it belongs in a bigger context, really, like starting almost like 3 or 4 years ago, where I somehow really got annoyed that compilers were so slow for generating fast gem kernels compared to any vendor library. So we started to integrate domain-specific optimizations, particularly for gem, and then as an extension to more general tensor contractions directly in this like LVM loop optimizer called Poly. And this was kind of how I initially got into the optimizing neural networks. And then this took over, like there were many domain-specific compilers in that space. One of many was this particular paper where we worked with IBM Research and Cornelius Croftis on generating code for an inference accelerator designed by IBM. Right. The idea is pretty simple. We take Polator compilation, in particular the constraint-based dependence analysis, and use that to derive a state machine that allows us to drive this local control unit of this accelerator, and that generates fast code. But this by itself is a neat idea, gives us a nice paper. I think the even more interesting kind of takeaway is that a lot of the infrastructure, the software infrastructure that we use there, in particular, it uses a library called ISL, which is a library for Polator reasoning, which we developed over the last 10 years together with Sven Berdolag in Polylabs. And so I think it really demonstrates the kind of research I really like, which is really like taking ideas and evolving with them, but then also then developing them into software stack that is actually robust enough to build. I mean, to really serve as a foundation for new interesting research projects. And so ISL was the foundation of that project. And we just recently published a paper at UPSA of a success of ISL called FPL, which again, we directly contribute to the MLI open source repositories. So I guess that this hopefully we're going to be the foundation for a lot more papers in this procedural space.
Great, thank you very much. I have a few more general questions. My next one is, well, maybe connected slightly with the ExCALIBUR projects. From your point of view, do you think that the scientific community is ready for the transition to exascale computing, or do you think we are a long way before we are going to be able to use efficiently exascale systems?
Yeah, I think I mean, I don't think I'm in a position to answer how good we are really doing as a community, but I want to share an observation and or maybe just as an answer really say that this really depends on particularly on the domain we're interested in, right? So if we count AI as a kind of an exascale domain, There's a lot of funding. There's a lot of like specialized hardware. So very specific for specific workloads, and then there's a specific I don't know, software hardware combination. I think that that's actually quite attainable and maybe already attained today. And other visible, more like highly visible, more classical HPC domains, maybe even climate modeling, that may not be so far away. But I think my key observation is that in general, like transitioning to these exascale machines, and in particular, if you use highly specialized hardware acceleration, this is an incredibly costly, complex problem. And currently, the most promising solutions are typically one-off solutions that have one specific domain, but only if this domain is large enough that an incredible amount of resources can be put into that domain. And so for me, I think on that question, really the interesting thing is that I think there's a big risk that we get an increasingly growing technology gap, where basically some highly funded domains really don't see exascale as much as a challenge, but there are like tens, hundreds of domains where we have amazing research potential, which just fall a little bit off the cliff. And I think these domains will just keep maintaining their CPU-based codes and run on like today's performance for the next decade. And I think this is a big challenge for us as a community. So I don't have doubts that we can get exascale to some communities. I think the big challenge to face really is, can we find a solution that basically as a global broad community allows us to get exascale to basically any household almost. And I think that is the challenge that's interesting to look at.
Great, thank you. My next question is more on the hardware side, I guess. But if you want to not restrict yourself to hardware, that's fine. You have been working a lot with computers in the last year, a lot along your career. If there is one thing you could change about high performance computing, what would that be? So I'm saying about hardware in particular, but if there is anything else you would change, what would you change?
So I think there are basically three answers, right? So first, let me answer the hardware aspect, right? So obviously, we want to go to more like both data flow architectures and more domain-specific hardware architectures. I think that's broadly accepted consensus in the community that specialization is one way to kind of keep delivering more performance. And AI, for example, a lot of AI accelerators demonstrated that seeing how we can use them for broader domains might be interesting. More on like going one meta level higher to actually really scale that up, like bringing more and more specialized hardware to our large software stacks. They are basically the two challenges. We need to be able to radically accelerate how fast we can develop faster hardware, better, more specialized hardware, but also how we can evolve our software stacks a lot more dynamically, right? And so finding, and that's coming back to what are the projects I'm working on. I don't think we can continue to think anymore in a kind of these isolated ecosystems. Mm-hmm. We say, this is a hardware design stack and this is a software science stack. So what's well known as this hardware software co-design as a kind of a concept, I think that needs to be almost inherent in our day-to-day programming. We need, I'm not even sure if the concept of a single programming language so much makes sense anymore. So I think over the next decades, these boundaries should become a lot more fluent. Having said that, and I think like MLIR, the circuit project where we developed with LLH, the Verilog compiler that all share a common foundation. Mm-hmm. All of these projects work towards kind of bringing these concepts closer together. But kind of moving a little bit away from your hardware or like hardware question, I think in HPC in general, we are very technology focused. And technology is really the driver of scalability in some way. But I think we often kind of overlook a little bit the social aspects. In particular, there are a lot of fears and kind of social structures that prevent collaboration. So just within a given domain, like different groups working on different projects, but in particular, if you want to really collaborate with hardware designers, collaborate with, really across, like radically across domains, we need to find a way to do that efficiently. And basically scaling HPC beyond the classical HPC community, I think this is by far the largest challenge we really have.
Great. Thank you very much. I have two more questions for you. My next one is a very general one. What are you curious about right now in your research or in HPC or in anything?
Yeah. So I use that to do kind of like I guess promote one of my favorite like side projects, which we founded maybe meanwhile almost 2 years ago at ETH, which is a project to work on like what we call scientific excellence and well-being. And it has a website, so if anyone's interested, you can just look it up with what's been done there. It's not large or highly impactful, but I think it has two really interesting ideas that might seed further discussions. The one idea, what I mentioned earlier already, is this kind of taking inspiration from domains like psychology, in particular sports psychology, where really world-class athletes already today train very deliberately, and in particular know how to not overtrain. But really like be at the performance optimal and a kind of like more maximal effort. And I think in computer science, a lot of us know this kind of concept of flow, where we program and then like effortlessly almost like and actually really relaxed and do a really good job. And then way too often kind of day-to-day stress prevents us from actually working in a both relaxed and productive state. And so I think, and that's why like I'm quite curious about like what Edinburgh does here, what people actually professionally and deliberately do in taking a little bit more consideration about how we work. I think that's as an idea is worth mentioning, discussing, and the second idea in that space is the idea of communication. I previously said it's important to scale across beyond our own community. And I think the other observation I really made over time is that a lot of us are extremely successful in what we are doing. And part of that success is that we learned a lot of tricks and personal like strategies to be efficient or effective in our community. And if we look back, most of us will have figured out these like powerful strategies via trial and error, often very painfully. And so over the last year, what we did together with ETH, we developed this unworkshop, we call it, which is a simple workshop meta format, which really just a couple of small games that facilitate communication and discussion about an interesting topic. And we use that to bring people together to just discuss some aspects of their scientific life, and hope that just due to people with interesting experiences and maybe clever tactics, people attending can learn a little bit more, that something that can help them to kind of improve their day-to-day life as a scientist. And I think this is really interesting. So yeah,
sounds very interesting. Sounds very interesting. Thank you. And my last question is about, so we are talking a lot about the transition to exascale computers these days, where there have been some announcement from Intel for the next generation. But what do you think is going to happen in terms of hardware in the next maybe 15, 20, 30 years? So do you think we are going to have still accelerators and CPUs, or do you think we will have to deal with a brand new generation of hardware?
Yeah, I mean, I think this is a really difficult challenge to answer, right? I mean, obviously it will be way more heterogeneous, way more complicated, like, I mean, not even chips, right? Like, I mean, network on chips, super heterogeneous, super diverse. That's for certain. I think it's really hard to say how or even if there will even be a kind of a standard architecture for HPC. I could almost imagine that we start to have really like domain-specific HPC clusters at one end of the spectrum, and then these like immensely large cloud computing resources on the other side, and then these kind of distinction between a classical HPC data center and cloud computing. Probably maybe it exists still, maybe it's, I mean, at least the software workloads may transition between the two, right? Suddenly you want to move it into the cloud, and you have also there again a very diverse ecosystem of both software and hardware, but then at the same time you may have highly specialized HPC clusters. So that's for certain. And the other thing is, I think HPC might become a lot smaller, right? So we managed to kind of get cell phones that run certain workloads, and I think we will certainly get classical HPC problems again down to the size of a desktop computer or something, such that, for example, I don't know, you want to use HPC to help with medical imaging. One of the things we look into exascale. Some computational algorithms like reverse time migration, which Paul Kelly and other people in Imperial work on, are not way too complicated for a cell phone or even a desktop computer today for medical imaging. But in 10, 15 years, I think that's perfectly like imaginable that these kind of algorithms run on a cell phone sized device with a local ultrasound device, and then we can do incredible imaging just with like mobile devices. And so really like scaling HPC from like mobile to like large scale cloud devices with highly heterogeneous hardware. Certainly a challenge.
Great. Well, thank you very much, Tobias, for your input and for your time for this podcast. It was very nice to have a chat with you, and we would like to wish you best of luck for all your future projects, and in particular this cross-cutting ExCALIBUR project that you have with Imperial College.
Yeah, thank you, Sylvain.
Thank you very much, everyone, for listening to this podcast. As usual, the recordings will be made available very soon, and you can find all the links on Twitter, and just Google UK Turbulence, and you will find the website, you will find the link for the podcast, and UK Turbulence is also our username on Twitter, so you can easily find the links. So thank you very much again, Tobias, and thank you everyone for listening, and hopefully we will see you very soon for a new episode. So bye-bye for me.
Ciao.